In our next section, we're going to begin to talk about the core components of MPLS switching, which is mainly going to be the label distribution protocol in the MPLS core, and then the BGP routing that is hopping over LDP. Now, specifically, we're going to take this into a couple different subsections. We're going to start with an example of what we currently have done before, running BGP over the core. We're going to introduce MPLS into it and see how that changes the behavior. And once we know what the final functional result is, then we're going to go back through the details, talk about what are the specific components of MPLS, and then also what are the specific components of the label distribution protocol. Now, beyond this, we will be coming back in much more detail later with topics like MPLS traffic engineering with resource reservation protocol, and then also doing MPLS labeling with BGP in inter-AS option B, inter-AS option C for both L2 and L3 VPN. But at least for core MPLS switching, we're mainly going to be focusing on label distribution protocol. Now, as most of you probably already know, one of the main reasons that we want to run MPLS to begin with is the size of the BGP table. That currently, with IPv4 prefixes, there's over 500,000 routes in the global internet table, and the IPv6 space is starting to grow in addition to that. And at some point, you hit the upper level resources on what the physical boxes can install in terms of not only global memory, but also the forwarding information base down into to the router's line cards. So the reason that this is a problem to begin with, though, is that every time we want to route an IP packet, all the routers in the middle must know where the destination is located. So this means within our particular case, not running MPLS, it would assume that all devices in the middle of the network from point A to point B need to be running BGP and have to have a specific route to the particular destination. Now, in our current example, though, the way that we have solved this is basically just by running BGP everywhere. So our goal was here that we have the core of the network in the middle, which was AS1, and we're essentially running BGP everywhere by configuring XR1 and router 1 as route reflectors. Okay, route reflectors for IPv4 unicast. We're not yet talking about VPN. And we have a full mesh of connectivity from the route reflectors down to the clients. And then we have the secondary route reflector likewise that is fully meshed to the rest of the clients. But some of these devices in the middle, for example, XR2, doesn't have sources or destinations that are directly connected to it from the point of view for BGP. So it doesn't necessarily need to know about every single destination as long as we can tunnel the traffic over the router. And in real deployments, where this comes in is when the service provider is trying to provide simply transit in not cell applications. Because there's a difference between an internet service provider and an application service provider, where the ASP might be a content delivery network that is sourcing video feeds or audio feeds, where the ISP's job is simply to get traffic into the ingress and out of the egress edge without having to do all sorts of inspection, all sorts of decisions on the actual traffic flows. So in other words, from the end client application's point of view, they're not trying to reach a destination that is inside the service provider. They're trying to reach a destination that is through the service provider, which ultimately affects how core routing works. So in the SP core, the only thing that we're concerned about is what is the ingress edge, so what is the entry point of the traffic, and what is the egress edge, what is the exit point of the traffic. The devices in the middle don't need to know the details about where the traffic came from or where the traffic is going to. And this simple principle is going to be the foundation for all of the other MPLS tunneling techniques that we're going to look at in terms of MPLS traffic engineering, in terms of L2 VPN, L3 VPN, that the idea is that the devices in the middle, we don't want them to have to make a decision based on the final destination. We only want them to make the decision based on where the traffic came in and where the traffic is exiting to. Now, the eventual solution to this is that we're essentially tunneling the traffic through the core. So, for example, we could say that we want to get traffic to come in from XR3 and then we want it to exit on XR1. Well, we could configure a GRE tunnel between the two of them, and then we could do our BGP peering over the GRE tunnel, And as long as the device in the middle, XR2, has a route to the loopback of XR1 and has a route to the loopback of XR2 or XR3, we should be able to tunnel the traffic through it. Okay, the same would be true if we were using an IPsec tunnel, or if this was a layer 2 network, if we were doing a .1Q and .1Q tunnel, a Q and Q. But in reality, the real solution for this is to run MPLS. That regardless of what the encapsulation is, whether it's GRE, IPsec, IP and IP, etc., the ultimate goal is that we're trying to make the middle of the network, the core, not have to make a decision on the final destination. Now, the way that we specifically do this, or why we specifically do it this way, is that MPLS has it has extensible applications that we can do besides just basic tunneling. And we're going to look at this in much more detail later when we look at the details of L2 VPN in terms of point-to-point pseudo-wires versus point-to-multipoint pseudo-wires, and then layer 3 VPNs, also hierarchical VPNs when we're looking at carrier supporting carrier and unified MPLS. But from the devices in the middle of the network's perspective, the logic is always going to stay the same, that they only care about the ingress edge and the egress edge. They don't care about the original source and the original destination. There's simply going to be label switching traffic as it is moving through the core. Now, specifically, the way that we're going to do this with BGP over MPLS in the middle is that first we need to run MPLS in the core, where in most typical cases, we're going to be doing this by running label distribution protocol in conjunction with IGP. But technically, we could use any labeling technique that we want. We could do static labeling, we could do BGP, we could do traffic engineering with resource reservation protocol. The ultimate goal is that we need some sort of binding between the ingress and egress edge devices, the provider edges, and MPLS labels. Now, we'll see a little bit later why we typically use IGP and LDP for this, because it's basically plug and play. But you theoretically could completely skip over LDP completely and use only BGP labels or use only traffic engineering labels. Okay, the end result is going to be the same, that we're forming the tunnel from the ingress to the egress. The next step is that we're going to form our peering. So we have a BGP peering that is somehow advertising the information from the ingress edge to the egress edge. Then when we go to make our decision on the BGP next hop, the key point that is going to change is that the next hop value is going to point us towards an MPLS label, which means that the traffic is going to hop over the devices in the middle by using the label value as opposed to the IP packet. Now, I talked about this briefly before, the importance of the loopback interface in terms of the BGP peering, because this is what is the destination of the MPLS tunnel. Now, we'll get into more details with that later in terms of troubleshooting and what things could go wrong if we're not using the loopback. But for the sake of the simplest example, assume that we're peering with the loopbacks in BGP, and those are going to be the next hop values that we're advertising the specific prefixes with. So this will assume wherever we're doing our peerings, like on router 2 as we're advertising the routes to XR1, it means that we're going to be doing next hop self. Or likewise, when the routes come in from 7 to 3, 3 is reflecting them to 1, and to XR1, it assumes that we're doing next hop self. Now, in addition to this, we're going to take some of these links that we have configured and remove them. So we're going to be transiting over devices that do not have BGP configured in order to get to some of these final destinations. So specifically what I'm going to do here is on XR2, we're going to disable these interfaces that go to routers 1, 2, and 3. And then on router 2, we're going to disable the interfaces that go to XR1. And then likewise on router 1, we have these cross connects turned off. So this means that if traffic is coming in from, and actually let's shut that one down as well, router 2 to 3. So this means that if traffic is coming in from 7, and 7 is trying to reach 10, basically it only has one potential path to go. So we're going to have to go the long way around this way. Okay, so we'll actually say that that interface there is shut down as well. Okay, so it would be simply, where can we do this? We can disable this one, and this one, and then here, here, and here. Okay, so 3 links we're going to shut down. So from 7 to get to the final destination, it means we're going to have to go the long way around, and we're going to be transiting over devices that are not running BGP. So specifically on router 1, I'm going to disable BGP, and then likewise on XR2. So first thing first, we're going to disable those interfaces. So let's go to XR2. And we're going to say on those particular links, which specifically are interfaces gig 0000.112 is shut down, .212 and .312. Then on router 2, these are going to be interfaces gig 1 to 11, 212, and 213. And then on router 1, we're going to simply disable the BGP process completely. So no router BGP 1. Now the end result of this from a BGP advertisement point of view should not change, because as long as we have IGP to provide TCP transport for the BGP sessions, we still should be able to learn the prefixes that we're advertising between the external autonomous systems. So for example, if we were to go over to router 8 should still be learning about router 10 and router 7 through BGP, because we have not broken the transport that goes from XR1 over to XR3, or from XR1 over to router 3. It just means that we have to route a different direction within the core. And specifically, we can see this from XR1 if we were to do a ping to 3333, or ping to 13131313, and ping to 2222, we still have a path to these destinations. They're just going a different path through the core. Okay, additionally, on XR2, we're going to say no router BGP 1 and commit. Now, this is one of the typical problem cases that we could get into now with BGP, that from a control plane point of view, it looks like that we have reachability to certain destinations, but traffic goes into the MPLS core and then for some reason is dropped. Where typically we'll see this later, the reason this mainly is going to happen is that if there's some sort of label binding problem, that you're advertising reachability to the IP prefix, whether it's through IGP or through BGP, but for some reason you're not able to bind the label to the next hop, or you're not able to bind the label to the final destination. So what I mean by this is that if we were to go to router 8, and from router 8 look at the show IP route BGP, from its perspective nothing has changed in the network. So we have this direct eBGP peering. It goes from 8 to XR1. XR1 has an iBGP peering that goes this way to router 2, goes this way to router 3, and from there we're able to learn the loopbacks of 10 and 7 respectively. However, if we go to actually send traffic to these and ping 7777 from our own loopback, we see that we don't have reachability to it. Now, beyond this as well, though, we're not getting an ICMP unreachable back, so we don't really know where specifically is the traffic getting dropped. The only thing we know is that the traffic is going out some direction, and somebody in the middle is dropping the packet flows. So we'll see once we get into larger scale examples of this, you need to know exactly how the step-by-step process connects, because when the control plane looks good, and you get to this very last step, you go to send traffic and you get ... you need to know where specifically are going to be the next steps in troubleshooting. Now, in our particular case here, from router 8's point of view, let's look at how are we learning the prefix. So if we show IP BGP for 7777, it says I know this through my external peer. Okay, the external peer is 10.8.11.1, which is specifically this interface here from XR1. Okay, 10.8.11. From XR1's point of view then, if we look at likewise where is it learning that prefix, and we show BGP, IPv4 unicast for 777/32, it says I know this as a best path through XR13. Okay, 13.13.13.13, previously based on this local preference policy that we had changed, we're saying XR3 is the preferred exit point out to AS7. So next thing XR1 says, well, how do I reach 13.13.13? Because I need to do that additional recursive lookup to figure out what physical interface, or at least what logical interface, does the next hop point to? So after we do the initial lookup internally, it says, well, how do I get to the next hop 13, 13, 13, 13? It says I know it through ISIS. Specifically, I know it out interface gig 0000.1112. The next hop value is 10.11.12.12. So this should mean that this next hop is a directly connected prefix. If we show route IPv4 for that particular next hop, it says it's connected on that interface. This also means that if we look at the ARP cache, we should have a MAC address entry for that particular hop. We encapsulate the packet in Ethernet, we put this as the destination MAC address, and we forwarded out that local link. Now the problem that we run into is that the neighbor on the other end of this link is no longer running BGP. So they receive a packet in, it says, okay, it has my MAC address, it's for me, now I need to figure out how to route it. So XR2 says, how do I get to the destination 7777? Well, I don't have a route. Okay, not only do I not have a specific route, if we show route IPv4, we also do not have a default route. So one other potential workaround for this is that maybe the core could fall back to a default match. So we have some sort of default collection point to a device that does have more specific routes. But in this case, the only thing that we know about is the internal routing information between the provider edges. Now, ultimately, we're not going to need, again, the destination information on the devices in the core of the network as long as we're able to go to XR1 and say, well, I don't need them to know the details of the destination. What I need them to know is, can you get me to the next hop? So can I ping 13, 13, 13, 13? And if I can I reach that over an MPLS label switch path? Now, in terms of configuration, since we're running ISIS in the core, there's basically only two other commands that we're going to need to use in order to turn the labeling functionality on. On the regular iOS boxes, which are routers 1, 2, and 3, we're going to simply go to the ISIS process and enable LDP autoconfig. Now, we'll come back to this in more detail and talk about what specifically does autoconfig mean, what are the different options for enabling the protocol. But for the sake of the simplest example, assuming that we're just enabling MPLS on every single interface. So we go under the ISIS process and we say MPLS LDP autoconfig. Okay, same thing on router 2 and router 3. Router ISIS 1, MPLS LDP autoconfig. Same as on router 3.